let's start. So, wait a second. I cannot switch slides. Okay, yes. So one thing is that diffusion-weighted imaging is used for multiple things, but one of very important is for the analysis of the brain. And one of the nice says on the brain, which is really complex, is that, well, if it was simple, we would not be able to understand it because our brain would be so simple. So it's a kind of paradox. So the brain is a very complex organ, and it's also very difficult to, so we don't understand a lot of that is going on actually in our brains, and there is a lot of developments on trying to understand how it functions and how it works. And what I will present today is a bit of a tool that is also being used to try to understand the brain. So if we look at imaging, we have magnetic resonance imaging, and which is one of the most commonly used modalities for brain analysis. So in the clinic, so we have for different modalities, T1, T2, perfusion, spectroscopy, all of them give different views on the brain tissue and the functionality of the brain. For example, a spectroscopy can give information about the chemical composition in areas of the brain, or functional MRI gives information about what areas of our brain are activating when we are doing some functions. So what are the functions on different areas of the brain? So magnetic resonance is a medical acquisition technique that is incredibly versatile and allows you to acquire a lot of different information. And what we will be talking about today, or I will be talking about today, is about trying to get an image of white matter in the brain and in vivo. So what is white matter? So if we look at the brain, we have different structures, but we could look at the brain as having two main structures. So the gray matter and the white matter. And the white matter is the connection between different areas of the gray matter. The gray matter is the outside of the brain, and the white matter would be the connections between these different functions. So like the processes and the cabling between them. So the only way some years ago to look at these structures was actually by opening the brain and making a resection, and then you were able to see the white matter structures. But for a lot of applications, you would like to be able to actually see this cabling, which is very important, without the need to open the brain. And this is what actually diffusion tensor imaging, or diffusion-weighted imaging, allows us. This cabling of this white matter is important, for example, when we have tumor resection. So a tumor has the tendency to move the white matter structures around, and it's not known in advance where these white matter structures are moving to due to a tumor. So without being able to visualize them, the surgeons are left to guess where the fibers have gone, or to do awake operations to detect where they are. And they are interested, for example, if you resect the tumor, to remove the tumor without damaging the main white matter structures. For example, the motor structure, if you damage that, then the person is paralyzed. So this is a very important part also of our brain, together with the function. So one of the problems that we have is that this fibers, these white matter structures, are very small, so are of the order of micrometers, and they are much smaller than the resolution of our in vivo scanners, which are of the order of millimeters. So this means that for each voxel or each structure that we have in the image, we have thousands of these white matter structures on it. So we cannot capture directly what is the structure, the anatomical structure in vivo using these scanners. But what we can do is we can measure what is called water diffusion. So water diffusion is the random movement of molecules and gases and liquids. And if we look at a glass of water, we can see that if I have a molecule, it will be moving randomly in this glass of water in all directions. And we could consider diffusion is the distance that a molecule, the probability that the molecule moves a given distance after a given time. It also depends on temperature and the type of fluid. So if we are in the middle of a glass of water, any direction has the same probability to happen. However, if we put some straws on this glass of water, then our diffusion becomes anisotropic. There are some directions that are more prominent, and we have more probability that the molecules will be moving in this direction than on the perpendicular direction, because in the perpendicular direction, we have barriers that do not allow that this movement goes there. So if we have the water diffusion information, we have kind of indirectly some information about the structure that is below. So in this case, if we can measure how is the diffusion of the molecules, this probability of getting of a molecule getting to a given distance in a given direction, we have a formula here, a kind of Gaussian formula, and we have this D. This is the diffusion coefficient that indicates how much we diffuse in a given direction. So if we are in an anisotropic behavior, this D depends on the direction we are taking the images. And we have this kind of representation of the probabilities, right? And each direction then varies. So this kind of information can be represented with what is called a diffusion tensor. So instead of having all these directions, we can simplify that to what is called a diffusion tensor. And a diffusion tensor is a 3x3 matrix, symmetric positive, that represents actually this behavior that I'm showing to the left. So this probability of the molecules to move a given distance after amount of time. So if we have this formula below, then this is what would represent how this probability, and the D, this diffusion tensor, gives the indication of how the diffusion is. So when we are doing our, so MR, it's able to measure or make measurements of this diffusion in given directions. And we can, I don't go in details here, but we can compare the signal that we obtain in each of these directions to the this diffusion coefficient that I talked before. And then if we have these diffusion coefficients in many directions, right, then we can fit a tensor, a diffusion tensor, which is this 3x3 matrix that I mentioned, that represents how the diffusion is behaving in this voxel or this location. Good. So if we do this with these elements, what we obtain is that we have a volume. So a volume would be a grid or a three-dimensional picture. But instead of having in each pixel, we call voxels when we are talking about volumes. Instead of having just one quantity, what we have is this diffusion tensor. Yeah. So this, in this case, the second order tensors that represents this kind of information, this diffusion information I said before. And the question is, okay, how can I visualize that? Yeah. So if we just take slices, so like the images that come out of the scanner, so I would look at this volume in slices, and then for each component of this matrix, I just put it next to each other. There is very few information I can obtain from this kind of visualizations, because it's very difficult to reconstruct just mentally how is the diffusion by just looking at these images, which I'm showing here in the matrix. So what you can see, for example, is that the ventricles in the diagonal are there, but it's very hard to do much more, to get much more information than this. One important thing when we talk about diffusion tensor imaging is to realize that we can apply eigenanalysis on this. So, well, if we apply eigenanalysis to our diffusion tensors, we will obtain eigenvectors and eigenvalues. I assume that this is clear to everybody. And what you can do is you can order your eigenvalues from larger to smaller. All these eigenvalues should be bigger than 0 because diffusion is always positive. So this is why it's a positive diffusion tensor. And what you can do, or you can indicate or analyze, is that if you have your main eigenvector, so the eigenvector which has the largest eigenvalue, this gives an indication of where there is the most of your diffusion, right? And if you remember what I talked earlier about the glass of water, this would give you an indication of the direction of your straws. So for actually in this diffusion tensors, we can make this calculation of eigenvalues and eigenvectors, and we obtain some information on the orientation of these ellipsoids and the amount of diffusions. And we will be using that also for the visualizations. Okay, so there are other models than the diffusion tensor that I'm talking now, but I'm just giving a bit of a basis of the visualization, and there is quite some work also in the visualization of this tensor data. So that's what I will be focusing next, and give a bit of an overview of the kind of methods that are being used to visualize this diffusion tensor imaging data. And there are these four main elements, so the scalar fields, glyphs, tensor fields, lines, and segmentation, and I will be talking a bit about each of them now. So one of the most common things that is being done also in the clinic is to go back to just having a scalar information or a scalar images. So basically what you do is you take this diffusion tensor, you calculate some property that you think is relevant, and you convert that back to a volume, a scalar volume. And this scalar volume can be shown with any visualization techniques that are used with the scalar volumes, which you will be also seeing in the during this week. Here I'm just showing one slice. So one a scalar value that is very popular is what is called fractional anisotropy. And what does fractional anisotropy compute? And this is the equation here below. It mainly computes how much the tensor differs from the spherical form. So it will be 1 if you are completely linear, so then your eigenvector, your main eigenvector is really large compared to the other two, and it's 0 if it's a real spherical tensor, right? So it's isotropic. So FA basically gives an indication where you have an orientation. This fractional anisotropy is limited. The fact that we reduce this diffusion tensor, which is a 6-dimensional entity, to just 1 dimension makes that you lose information, of course. These are usually invariant, so these are independent on rotations. But also in this case, for example, the fractional anisotropy, what it does is that it measures how different you are from spherical, but this can be linear, like I'm showing here below, but you can also get that you have a disc-like diffusion, so you still will not have a preferred direction, but you will be on the plane, and this fractional anisotropy is not able to discern that. So there are other techniques that has been computed, or other anisotropic measures that help you to overcome a bit this, like you compute also other kinds of anisotropy to be able to also identify when the anisotropy is planar or so. And these are one of the similar ones. So if we look at the scalar field visualization, basically the visualization itself is easy. This is between question marks, so because still visualizing volumetric data is not trivial, but you reduce your 6-dimensional information of your tensor to just 1 dimension. So you are missing a lot of information. Another common way to do that, to visualize the data, is using the main eigenvector. So, and this is very popular in the medical world, in which you basically take the coordinates of your main diffusion vector, this eigenvector that have larger diffusion, so it gives an indication of the fibers, and you make a direct mapping to RGB. And then you visualize that on your slides, and then you get these colorful images like this. So this is rather simple. It shows directionality, but it has the problem that you see very well the main orientations of the brain, left to right, front to back, and bottom to top. But if it's anything in between, it's harder to inspect. And you still simplify your information, of course. So another very common method to visualize the data is then going into the tractography. So actually really trying to reconstruct your fiber structure. And there are many algorithms that are developed to go from these diffusion tensors into fibers. And there is a lot of research being done on doing that in a reliable way. I will just talk about the most simple one, or the most commonly used one, which is the streamline tracing, which is also very similar to a stream, which is based on the streamlines that are being commonly used also in flow visualization. So basically what you do is you try to integrate, you see your field like a vector field, and you try to integrate through it. Yeah, so you say that your vector is basically a tangent of a path of the molecules or the fibers that are forming your data. So basically what you do is you do an integration of this vector field. To be able to do this integration, you need to put initially a seed point, and then you follow this vector field, which is the eigenvectors are bidirectional, and you follow it, and this is a reconstruction of your potential fibers, right? So a common way to do this numerical integration is using Euler forward, which is basically you have a point, you calculate what would be the vector there, you move a step, and then you do the same with the next, you calculate, you move a step, and you do the same, right? Often this numerical integration using Euler forward, people who knows it's not very accurate. So usually you would at least go to second order integration schemes like Runge-Kutta second order, where basically you do a bit more complex integration methods. So you make a step, you calculate, you average, and then you really move on the next step, such that you get a more accurate paths, right? So so if we apply this method, we are putting seed points, so we have to do this initialization, and then we can calculate all these fiber tracks, right? So we calculate these fibers. One important thing to realize is that we stop these fiber tracks when our tensors do not define well a direction. And this is usually when our fractional anisotropy is low, or our some of the measures I showed before are low. So when we have these fibers there, we can show them in different ways, right? So you can use just lines, but you can use illumination to make them, the geometric structure of these lines, more clear, or you can use you can use tubes, or you can also use the other eigenvectors and eigenvalues to show what is the information in the other directions, showing hyperstreamlines. So basically you have tubes in which the size of the tube changes depending on the other eigenvectors and eigenvalues. Because when you do tractography in the way I just described also, you also lose information, right? So you are just following the path, so you are just following the main eigenvector and you are disregarding the other directions. So if we have these tensor field lines, shows more global information, right? Because we are looking, so we are reconstructing more what a doctor or a clinician or anatomist will expect that the white matter looks like. So do we reconstruct these structures? Still, the method I'm showing is simplifying, so you don't show the full tensor, you are showing a simplification by the vector. And we need to have all this initialization, which if you don't put the seed points in the right place, you might be missing important information. And we are doing all this integration, which of course adds error and accumulation. And if we have a lot of seed points, we also have a lot of cluttering. Another common method that we have in visualization, or something happened here with the eigenvectors, it should be an arrow. So is to show glyphs. So glyphs is basically you show the geometrical information at each position. So basically in a glyph, what you do is you don't simplify the information, but I'm showing the tensor information at each location and I show it fully, right? So I'm trying to show the full information that is there. And the common, I already have been showing glyphs, right? So the ellipsoid is one of the most straightforward ways to show diffusion tensors. Yeah, and this ellipsoids represents a constant probability of what the probability distribution function that your diffusion tensor is representing. So you have this surface that you are generating by the formula that I'm showing here. And these are basically the ellipsoids. The ellipsoids, however, have some limitations. I'm going to go a bit faster. So there are some properties you want to preserve in your ellipsoid, in your glyphs. And the ellipsoids have some limitations that, although your tensor might be very different, when you look at them, they might look very, very similar. Here is an example. So you are looking at different tensors. The T1 to T8 are different tensors, and they are looked at from different views on the top, and the second is from another one. And you can see in the view 2 that they look pretty much the same. And this is why other visualization glyphs have been developed to help understand better the data. One is, for example, the cuboids. The cuboids have the problem that they show the orientation very well. But when we have, for example, a spherical diffusion tensor, you don't have a clear orientation actually, right? Because when we have a spherical, any orientation is valid. And if we use cuboids, then what happens is that we are putting an orientation that is actually not there. So this is not a good glyph representation of the data, right? So Kindelman proposed what is called superquadrates, which tries to combine the advantages of having a very clear orientation when it is there and not having the orientation when it's not there. And also it generates this disambiguity that actually the ellipsoids have. So if we look at the example I showed before and we use it with superquadrics, we can clearly see that with the superquadrics, we see these are different tensors, while if we look at the ellipsoids, this was not visible. Yeah, and that's from the first view, you could already see it there, but now looking at the superquadrics, you see it more clearly. Okay. If we have glyphs, one important thing to consider when you do the visualization is where you put your glyphs. So it's important that you realize that if you put the glyphs in the grid, the structures you see are basically the structure of the grid beyond the structure of the data. So there have been also quite some work developed such that you kind of try to get rid of the grid structure such that you can clearly see the structure that is really in the data, and this is not occluded or cluttered by actually the grid. So the placing of the glyphs is also very important. So glyphs is another way to look at the diffusion tensor data. It shows the full information, but this information is very local in relation to the fiber tracks where we had these global connections. The glyphs show the full tensor, but they are very local. And if you want to look at a lot of them, you get really easy with a lot of clutter and things on top of each other and just see the external views, right? So there are strategies that you have to do to actually look at this kind of data. So often glyphs are more for detailed information and not so much for global information. Yeah, so given the time, I will not go in a big detail here, but I just want to mention that one of the biggest problems you have is when if you would do, for example, fiber tracking of the whole brain, you get a spaghetti pot like the one you see here. So you need to find strategies to be able to make this more structured and that it reflects better the bundles and the white matter structure that is in the brain. And for doing that, often people are using segmentation of tensor lines. Doing segmentation has several problems, like defining what things that are similar, what is different between the lines. That's not so trivial, right? There are multiple algorithms that try to deal with this. And you obtain then different, you can, by segmenting automatically some of these fiber structures and then using some strategies visualization-wise, you are able to discern or to facilitate the exploration of these data. So the seeding point strategy is one, right? But you don't see the overall and you can miss important information. But if you show everything, you can miss data. So if you show everything, everything is very cluttered. So then you need to use some kind of strategies like segmentation to be able to look at that. But often it's difficult to find or achieve good segmentations of the data, also with the difficulty of finding good ground truths. Good. So I went very fast a bit, also due to time, through the different aspects. I hope it gives you a view on what are the different kinds of visualizations that you can use if you want to work with this kind of data. There are multiple applications of it. It's not just also for the brain. So since the diffusion-weighted MRI has been developed, more and more, it's a whole field of research also from the clinical side where you can apply it. And it's not just in the brain, but also, for example, for a study of the heart and the muscles, because these are also very thin fibrous structures that are difficult to capture otherwise and have multiple applications. Yeah, so overall, I talk about diffusion-weighted MRI, but I just basically present diffusion tensor imaging. That is a specific model that you apply. There are more complex models and more complex visualizations that you need for this, but I could not handle that in this time. So I focus on diffusion tensor imaging, and I have given a glance of the different possibilities that are there. But this is rather just the basis. There are many more literature and work on that. We have a recent overview on diffusion MRI visualization. There are also other overviews and a state of the art. So yeah, maybe it's good if you are interested that you have a look to that. And with that, I would like to finish my presentation. Sorry.
Thank you very much, Anna. So I see already here on Discord, we have a lot of questions. So I will just ask a couple of them. And then if you have the kindness to take a look there, maybe some people...
I'm not in Discord right now, but I will try to connect.
Okay. So the first question that we have here is how regular is the typical measured tensor field? Is any kind of a denoising step necessary before tracking the fibers?
Yeah, so yeah, in general, when you do the model, right? So when we do the acquisition in different directions. And actually, if you want to have a tensor, you just will need 6 directions of acquisition. But actually, in practice, you acquire many more directions. And when you are actually fitting your tensor, you are kind of already applying a denoising. There are other models that are more complex that you apply. There are also, yeah, so there is noise, of course, like there is in any imaging, and then you have also denoising and image processing approaches that are specific for this kind of data. In our case, we usually don't apply any more cleaning steps than this one. You have to do some corrections from the acquisition. This is because of the type of measurement is being done and some registrations or so. But once you have the signal, we don't apply any extra denoising to it for our applications.
Maybe one more question. I love glyphs, but from your personal perspective, how often do medical professionals actually make use of them, and in what specific context?
Yes, so the thing is that with diffusion tensor imaging or diffusion-weighted imaging, they need to use this because there is no other. They need to visualize or to transform the images to something that they can understand and visually represent, and the 3D structures of the fibers. So in our collaborations, for example, when we are working with neurosurgeons and they do use the visualization, really the 3D visualizations like the fiber tracks that I was showing, to really interpret the data, because they don't have any other way to do that. The tensors themselves, the kind of glyph visualization, are often more for acquisition, people who work more on the sequences or that are doing more research-oriented kind of work. So yes, they do use the visualizations, because in this kind of modalities, there is no other option actually, right? So you can do it more simple or more complex, but at the end, you need to have a visualization. You cannot look at the raw image just and make sense of them.
Okay. And the last one, so here Sam is asking, do you have any questions, any suggestions for where can one obtain raw data files to start playing around for ourselves? What are visualization software packages or applications you use to visualize the data presented in your slide deck?
Yeah, so so we have our own tool that we developed a while ago. It's called Vista. So that's what I use for my the things I showed here. But there is MRTrix, and MRTrix is also a very common tool used nowadays to visualize this kind of data. Also, if you look at 3D Slicer, also have modules that allow you to visualize data. So there are multiple tools out there that allow you to make basic visualizations of this type of data. And concerning whether you can find, yeah, so there was, now I will not find the right name, but there is an initiative which is the brain, I don't call now to the name, but it's a big European project on brain, and all the data they have, it's available, and there are a lot of data sets there that you can use for analyzing and getting started.
Okay, well, thank you very much, Anna, for your talk.
Thank you.
If you have more questions, both to Anna or to Wonky that gave the talk before, please put them on the channels, and I hope that they will do their best to help you out. So
yes, I'm going to the Discord channel now. I will try to answer. Thank you.
Thank you.